Alrighty, hello year 11. So we are starting our next topic, which is electric circuits. So we are going to go through page 102 up to page 107, because page 108 is the start of your questions. If you don't have a textbook, I suggest you buy one, because this is how the format of your lessons are going to be now. Me reading bits and pieces from the textbook that you need to know. And I suggest you have your textbook open while watching these videos so you can actually see what I'm reading and what parts I'm pulling out from your textbook that you absolutely have to know. I also suggest doing this with a highlighter, highlighting the important bits. So, notice in your textbook at the beginning of each sub-chapter, there is a blue box. That is your learning that you must know. So in this case, it's for potential difference and electric current, its atoms contain positively charged protons and negatively charged electrons. Objects become charged when electrons are transferred from one object to another or redistributed on one object. Two like charges exert repulsive forces on each other, whereas two opposite charges exert attractive forces on each other. You need to be able to describe electric forces between like and opposite charges, explain various phenomena involving interactions of charge, and explain how electrical conductors allow charges to move freely through them, whereas insulators do not. Alrighty, so first thing you need to know, like charges repel and opposite charges attract. That's the basics of this unit. If two items have the same charge, they will push each other away. If they have opposite charges, they will attract. Okay? Simple as that. Okay, so that's pretty much about it. That's the summary of the first page. Okay. So now okay. Alright. So we know that an electric charge is a fundamental property of matter and responsible for the electrostatic interactions between electrically charged particles. First discovered with amber, being able to do this when rubbed with straw, wool, or fur. So basically you can get amber and you can create a static charge with a rock, which is pretty cool. That is pretty cool. Okay, so amber, rub it with some sort of fabric, it creates a static charge, it can then attract things. Yeah. And I'm sure you've all seen the experiment where you have two rods, you charge one and not the other, and they can stick together. If you charge both, they'll repel each other. If not, we will do that in class next week. Okay? So, as you know, positive charge, negative charge. These are effectively, if something is positive charge, it means it has less electrons. If something is negative charge, it means it has more electrons. As you know, protons, positive charge, electrons, negatively charged. We have, I'm sure you all know what atoms look like. If you continue going into this into year 12, you need to be able to draw an atom diagram. So we have a simplified version of an atom versus a more complex version, and you're going to be saying, Miss, there's less drawing on that. Yes, because atoms are actually in a cloud, not nice circuits, and they're constantly buzzing around and bumping into each other. So they have the negative electron cloud around the positive nucleus. Remember, in the nucleus there are neutrons and protons. Neutrons have no charge, protons have positive charge, and they just sit together. Alright, so for electric charge, the standard unit is a coulomb. Okay? Named after the guy who discovered it, who was a French physicist. So, coulomb has the symbol of E. It's just a straight up E. Sorry, that's not a coulomb, that is electron, sorry. So an electron has the charge of negative 1.6 times 10 to the negative 19. See? Oh, so coulomb is the unit. Okay. Coulomb is the unit that we use for charge. An electron has negative 1.6 times 10 to the power of negative 19 coulombs, and a proton, which should be given, which we don't have a symbol for, is so a proton and an electrons are the exact same, have the exact same charge. Okay, so electron, that's an E, equals negative 1.6 times 10 to the negative 19 coulombs, and a proton is positive 1.6 times 10 to the negative 19 coulombs. Okay, since the magnitude of charge on an electron is so small, it follows that the number of electrons given as n in one coulomb of charge is enormous. In fact, one coulomb of charge is equal to the charge in more than 6 million trillion electrons. So, number of electrons in one coulomb, kind of like Avogadro's number, we have one for physics. We have the number of electrons given by a capital N is equal to 1 divided by 1.6 times 10 to the negative 19, which equals 6.25 times 10 to the 18. Okay, so in electric currents, when you're using the N symbol, it is equal to that, and it comes from one coulomb being coulomb doesn't like a word, coulomb being divided by the charge of an electron. Okay, so one coulomb is a significant amount of charge. Even a powerful lightning bolt only delivers 30 coulombs. Most objects charged by rubbing have a charge in the micro and nano coulomb range. Okay, they're very, very small. Alrighty, next, electric charge. So you know that we can create a static charge. However, there is also something called the law of conservation of charge. So when you create static electricity and you're rubbing two things together like glass, like you had a balloon and you rub it on your t-shirt, to make the charge, one thing is going to become positively charged, the other thing is going to become negatively charged. So when you put the two together, the net charge, so the overall charge, is 0. Now usually the thing that is getting rubbed, so either the balloon or the rod, becomes negatively charged, and the thing that becomes positively charged is the thing that was being rubbed on, whether that be a piece of fabric, your shirt, whatever. Okay? So you remember, charges separate, electrons move to the item. So in the balloon case, the electrons would move from my shirt to a balloon, and then the balloon would be negatively charged, and I can use it to attract things like you do with your hair. Okay, next, triboelectric charging. So when two materials are rubbed together, the magnitude and sign of the charge acquired by each material depends on how strongly it holds onto electrons. If silk is rubbed against glass, the glass acquires a positive charge. It follows that electrons have been transferred from glass to silk, giving the silk a negative charge. However, if silk is rubbed against amber, the silk becomes positively charged as electrons pass from the silk to the amber. These results are understood by referring to figure 2.07, which shows relatively charge due to rubbing, known as triboelectric charging for different materials. Interesting. Silk goes glass. Silk is rubbed against glass. Okay, so looking at the table in your books, because glass is more likely to be positive and silk is less likely to be positive, the silk becomes negative. By comparing silk to amber, amber is more likely to become negative, so the silk becomes positive instead, which is, by all intents and purposes, quite fascinating how that happens. Kind of like the reactivity scale in chemistry. We have an triboelectric scale in physics. Okay, so the higher the position of material on a table, the more readily it loses electrons and becomes positive. Similarly, the lower the material's position, the more readily it gains electrons and becomes negative. Okay, I'm not going to read all of that because that is a lot. Charge separation. So, charge separation, that's static electricity where one thing gains a charge, the other thing loses. Well, one thing is a negative charge, the other thing is a positive charge. So charge separation also occurs when two objects collide. Boom. Okay, for example, colliding crystals of ice in a rain cloud cause large separation that may ultimately result in bolts of lightning when the charges are brought together again. This process occurs within rain clouds when lighter ice crystals moving upwards collide and transfer electrons to heavier ice crystals moving downwards. So basically how lightning is made. Okay, the transfer of electrons between ice crystals causes a buildup of negative charge at the base of the rain cloud and a positive charge at the top. The electrons at the base of a rain cloud repel electrons on the top deep into the ground, resulting in a positive charge on the Earth's surface. Charges then flow between the base of the cloud and Earth's surface, producing a large electrical discharge called a lightning strike, as shown in figure 2.09. That is very cool. So in the first part of the figure, you can see the clouds been separated to positive at the top and negative at the bottom. And that attracts the positive ground and the lightning strike, and then the charges are then shifted around. Okay. Next, charge polarization. Okay. So we know the opposite charges attract, but it's also possible for a charged object to attract small objects with zero net charge through a mechanism called polarization. Polarization is the separation of a charge in an object, forming distinct regions of positive and negative called poles. You know, like a battery or a magnet, they have poles, north and south poles. Okay. So look at figure 2.10. So a negative charged rod is held close to an enlarged view of a neutral object. Atoms near the neutral object surface become elongated because the negative electrons are repelled from the rod, while the positive protons are attracted. As a result, a net positive charge develops near the rod's surface, as the atoms positively and negatively charged becomes polarized. You can do this with water, which I will do probably on Thursday. Actually, no, probably next week because you guys are doing your D&Ds. Next week, we will look at charging water, moving water around with it being polarized. Okay. The force produced between the charged and neutral objects is always attractive, as illustrated in figure 2.12. When a positively charged rod is brought near a neutral metasphere, the negative charges at the top of the sphere are more strongly attracted to the rod than to the distant positive charges which are repelled. The result is a net attractive force between the rod and the sphere. This polarization forces arises because the charges in the middle are slightly separated, not because the rod and metal are oppositely charged. Had the rod been negatively charged, the positive charge would move to the sphere's upper side and negative charge to the bottom. This would again lead to an attractive force between the rod and the sphere. Thus, polarization between the charged object and the neutral one is always attractive. Okay, so you have a charged thing, you have a no charge thing. You bring the charged thing close to the no charge thing. The no charge thing is not charged, it's neutral. If the charged thing is positive, it brings the negative parts to the surface. If the charged thing is negative, it brings the positive parts to the surface, and they attract each other like a magnet. Okay, next we have insulators and conductors. I'm sure you guys all know what these are. Insulators are very bad at conducting electricity. They stop it from happening. Conductors allow electricity to flow through. So in insulators, I'm sure you know about valence electrons, which are if we go back to the shell model of atoms, there are something called valence shells or valence electrons, which are electrons that are free to move around. In insulators, there are very few valence electrons. They're all very tightly bound together, so they don't want to give up any of their electrons. They're quite content. Whereas in metals, and conductors in general, there are more valence electrons, so the electrons are easier to move around more easily and are happy to flow throughout it. Yeah, that's pretty much it. Between insulators and conductors. Insulators, very few valence electrons. Electrons don't want to move around, very stable. Poor at conducting electricity. Conductors, lots of valence electrons. Electrons are happy to move around, great at conducting electricity. Once again, there is also a scale for that, which is not in your textbooks. Great. Right. And we will stop there because then it's just a bunch of questions. Right. That is all. Goodbye.